Good morning, my YouTube viewers. It's Crystal here. Sorry it took me so long. I was just waiting for the screen recorder to start working, and it didn't work for the first 10 seconds, and then suddenly it kicked in. I wanted to do another video for you, and this video is going to be how to make a uniform distribution and test it using Python in Excel. And basically, if you've been watching my videos, uh, what has happened is because I've got this spreadsheet that's got lots and lots of information on it, lots and lots of pages, and because the spreadsheet has got lots and lots of pages, it's making it difficult for Python to work, which is sad, really. So basically, Python in Excel cannot accept a lot of formulas. It sort of like clogs up the system. So what I had to do was I had to make a blank file called work in progress and copy the page over to work in progress to get it to work. And that's why definitely yesterday, I was having problems getting the program to work. And so that's another problem that you're going to have working with Python in Excel, whereas it won't accept a lot of data, which is sad, really, because I don't think that I do that much. I'm not a super duper scientist, and I don't have tons and tons of code, but that's just the way it works. So I'm just taking the page and I've copied it over and to this work in progress file just so I can make this video. And so what we're doing is we're making a uniform distribution. So as you can see on the page, I've made 3 uniform distributions. And so we'll look at the code for the image. And we'll look at the code for the image, and this is for your uniform distribution. So you set your lower bound to 0, your upper bound to 1, sample size is 1000, and then we create the distribution, and uniform 1 equals NP random uniform lower bound, upper bound, sample size, and then we plot the distribution using matplotlib, and plt.hist uniform 1 edge color equals black, plt.title uniform distribution, plt.xlabel is bounds, plt.ylabel is frequency, plt.grid is true, and plt.show. And so that's the code for the uniform distribution, and I made 3 uniform distributions just in case I would need them. I also, just to see what the means were, I also tested the means of the 3 uniform distributions, because a lot of these hypothesis tests check the means. Not all of them, because some of them check the variance, but a lot of them check the means. So I did that. So mean 1 equals uniform 1 dot mean, and then you type mean 1 to get mean 1 to be printed in the cell. And so you can see the means of all of the uniform, you can see the means of all of the uniform distributions, and you can see that they're very similar. So we've got an alpha of 0.05. You could have an alpha of 0.01 or an alpha of 0.1 if you wanted, but most people use an alpha of 0.05. Your null hypothesis is that the samples are the same, and your alternate hypothesis is that samples are not the same. I'll just say A here. You can say A or 1, but I like A. And then we performed 3 tests: the Anderson-Darling test with SciPy, and the Anderson-Darling test with stats models, and the kolmorogov-smirnov test. So basically, the test that I'm the most familiar with is the kolmorogov-smirnov test. And the thing is because I use that when I enter Kaggle competitions. And what you do is you're checking to see if any of the columns of data or features are not from the same distribution. And if they're not from the same distribution, then it's going to be difficult to get a good prediction. So you could delete them if you wanted to. If you had lots and lots of columns of data, and it doesn't matter if you delete it, you could delete those columns of data. The thing that we had with the Anderson-Darling test with SciPy, the Anderson-Darling test with SciPy doesn't give you the p-value. And when it doesn't give you the p-value, well, that's generally what you're working with when you're doing a hypothesis test, is you're looking at the p-value. So, but you've got the Anderson-Darling test with stats models, and that gives you the p-value. So the Anderson-Darling test with SciPy, I had to get the code for the p-value because it doesn't give you it with SciPy, which is strange, really, because the p-value is what you use for the hypothesis test or to check the probability. Your p-value is actually a probability. So I'm going to go over that Anderson-Darling test, but you can see the p-value is the second value, and you can see that the p-value is giving you a false negative because the p-value is less than 0.05, way less than 0.05, and so it's giving you a false negative. And so I thought about whether I should just take the Anderson-Darling test out, but I'll go ahead and give you the code even though it's giving you a false negative. And so that's something that you have to be aware of. Like whenever you're doing hypothesis testing, you need to make sure that you choose the correct test. So we'll just look at the code for Anderson. And another problem I had was whenever I had the hypothesis test on the first row, which meant the hypothesis test was actually going to be on the second row, it kept saying that the uniform distribution 2 wasn't and 3 wasn't defined, and that wasn't true either. And I don't know if that was because my Excel program is just clogged up and it was just doing that because it was clogged up or what. So that's why I had to take the test and move it down to the second row just to get it to work. So these are some glitches in the system that are going to have to be worked out, because until people are allowed to have really big files, really big Python files in Exxon, this is just really going to be an experimental program. And from what I understand, Python hasn't been rolled out to all the Excels. So there's a lot of bugs that they need to work out to get Python, to make Python readily acceptable to the public, because I'm not a genius, and I don't think that my programs are that big, and I just had a lot of pages because whenever I do something, I put it in a different page. So that's going to have to be dealt with if Excel wants Python to be a success. So we're going to look at the code for the Anderson-Darling test with SciPy. So perform the Anderson-Darling test. Result equals Anderson brackets uniform 1 dist equals norm. So it's only doing it on uniform 1. It's only checking it on uniform 1. And AD equals result dot statistic times 1 plus dot 75 over 50 plus 2.25 over 5. And I don't know. That's just what the code I got over one of these webs that I got from one of these websites, and I'm not sure. I mean, you could probably just say AD equals result statistic. If AD is greater than or equal to zero point 0.6, P, that's your p-value, equals math.exp 1.2973 minus 5.709 times AD minus 0.186 and AD to the square root of 2. And then if it's greater than or equal to 0.34, you get another formula. If it's greater than or equal to 0.2, you get another formula, or else it's going to be P equals 1 minus, and you get another formula. And then so what we do is we print off AD and then P. So this is the code that I was able to get from the internet to be able to compute the p-value, because it doesn't give you the p-value automatically. What I could do is see what happens. So I don't think it makes that much difference. They're both like really low numbers, and I don't think it makes that much difference whether you're going to use the AD equals result dot statistic or you're going to multiply it by something. So both of them are really low numbers. So you can, if you want to do some more research, you can do some more research, but this is just the code that I got off the internet to calculate the p-value from Anderson, Darling, and SciPy. So now what we're going to do is we're going to use Anderson, Darling, and stats models. Anderson, Darling, and stats models is much easier to use because it just says statistics p-value equals normal underscore AD uniform 1 axis equals 0, and then you print off the statistic and the p-value. So if you want a p-value, then maybe it's better to use the stats models. And then now what we're going to do is we're going to use the kolmorogov-smirnov test, which is the one that I'm most familiar with. You can use it for a 1 sample or for a 2 sample. I used it for 2 samples, but if you want to use it for a 1 sample, there is the code for 2 sample, which it would be KS underscore SAMP. But since we're using it for 2 samples, so it's statistic p-value, comma p-value equals KS underscore 2 sample, uniform 1, uniform 2, and then you print off your statistics and your p-value. And so that's really what we get for the Kolmorogov-Smirnov test. And so Anderson-Darling's a bit iffy. I definitely wouldn't use it with a uniform distribution because it's definitely giving you a false negative. The Kolmorogov-Smirnov test looks okay. It's giving you a true positive. And then there you go. And then so we're just making the distinction between a 1 sample test and a 2 sample test. So that's it for this video. We've covered the uniform distribution, the means of the uniform distribution, the null hypothesis and the alternate hypothesis. We've covered false negatives, because I believe the Anderson-Darling test is giving us a false negative, because the samples are pretty close to the same. So the Kolmorogov-Smirnov test gave an accurate reading, but the Anderson-Darling test didn't. But I went ahead and included the code for you just in case you want to use it and try it out. And thank you so much for watching this video. I'm going to conclude. I'm going to stop it here. If you like my video, please like and subscribe. And thank you again for watching my video. And I look forward to communicating with you in the next video.